Welcome to SnowEx Liquid Solutions training module, using liquids to protect the environment and your business. In this module, we will explore the environmental impacts of oversalting and how that is driving regulation and public demand for more sustainable winter practices. We will examine the root causes of the problem and the relative responsibility of the commercial and municipal snow and ice sectors. Lastly, we will discuss how liquid approaches can mitigate those outcomes and the risk management benefit of adopting sustainable salt practices sooner than later. The impacts of oversalting from winter services are outpacing development and are now reaching unsustainable proportions. The following scenes are familiar to all who live in the North American snowbelt: the deterioration of our highways, vehicle and infrastructure corrosion, soil erosion, crop and foliage damage, and most concerning, the irreversible pollution of our rivers, streams, and lakes. The resulting damage is rapidly outpacing resources to repair and replace it. By all estimates, it costs taxpayers a minimum of $1,800 per ton of salt spread to repair damage to infrastructure, foliage, and ecosystems, and that is for the damage that can be repaired. The watersheds are becoming increasingly vulnerable to rising levels of chlorides from the runoff from salting in winter services. According to the USGS, river chloride levels in the northern urban areas have more than doubled in the past 20 years. The public is becoming increasingly aware and demanding action. To get an idea of the enormity of the problem, consider that just 1 teaspoon of salt permanently pollutes 5 gallons of water. 50 pounds of salt pollutes 10,000 gallons. In 2014 alone, over 19 million tons of salt were used for winter de-icing. Most of that salt is now in our water. The next series of slides is intended to explore the scope of regional impacts, causation, and the extent of the public response, effect, in order to provide insight into how this problem may impact the snow and ice industry in the coming years. In his presentation at the 2015 APWA Snow Show, Paul Johnson, operations manager in Wellington, Ontario, pointed to the chloride problem in one Ontario stream, which at peak winter months tested for 20,000 milligrams per liter for chlorides. To put that in perspective, that is almost 100 times the chronic level for chlorides in fresh water established by the EPA. During the winter, that river is more suited to sustaining this type of life than this. This is an extreme example, but keep in mind that chloride levels above 800 milligrams per liter are harmful to most freshwater aquatic life, and a 7-day exposure to 1,000 milligrams per liter is lethal to rainbow trout. This issue is of particular concern in Canada, where more than a third of the population relies on groundwater for drinking, including the entire populations of Prince Edward Island, Kitchener-Waterloo, Cambridge, and Gulf. To meet this problem, the Smart About Salt program was established to raise public awareness and to train winter maintenance professionals in sustainable salt best management practices. In Milwaukee, Wisconsin, the red areas on this map indicate higher chloride levels as you get closer to the more populated areas of the city. These graphs show how much the chloride levels increase in the winter in the 3 monitored rivers. Note the chloride levels in the Kinnickinnic reach the acute 800 milligram per liter level harmful to most aquatic life in the winter, and remain above the chronic threshold established by the EPA in the summer as residual salt on the ground continues to contaminate runoff. Concerns for water impacts led Dane County and the City of Madison to establish the Wisconsin Salt Rise program to educate the public and train public and private providers, homeowners, and businesses about sustainable salt practices. Many regional businesses that hire winter contractors have signed on to the effort to support and spread the message. In Minnesota, again, the major water quality issues in red are centered in the highly populated Twin Cities metropolitan area. There are 41 waters that have been determined to be high risk for chlorides. 1/3 of the monitoring wells have chloride concentrations greater than the EPA guidelines for drinking water. Starting a decade ago, Minnesota, the land of 1,000 lakes, realized they needed to do something to address these escalating chloride levels, and they established 2 certification courses, one for municipal providers and another for private sector providers who service parking lots and sidewalks. Since established, over 6,000 providers from 8 states have taken these courses. These manuals and best management practice training courses are now modeled by states and municipalities across the snow belt and are available online for anyone to utilize. In New Hampshire, an $800 million I-93 highway expansion project is being held up because of the chloride levels in the watersheds along the highway, which were to have been addressed as a part of the funding agreement for the project. As of last summer, the fourth lane in both directions was to remain closed until a solution to the chloride problem was reached. A 2008 study to determine the chloride loading to those watersheds attributed runoff from parking lot services by the private sector to be 50% of the root cause. In 2013, New Hampshire moved to address the problem by establishing the Green Snow Pro certification program to train private and public providers on sustainable salt management practices. They also passed legislation providing protection from liability related to winter services to certified providers and property owners who hire them. Almost 1,000 providers have taken the certification since it was established. The Minnesota Pollution Control Agency and New Hampshire Department of Environmental Services both publish a list of certified providers on their websites. In Upper New York at Scenic Lake George, the crown jewel of New York outdoor recreation and a major source of revenue in the state, chloride levels have tripled in 30 years. Concerns for the irreversible impacts of this trend have led to the establishment of the Fund for Lake George, which has mounted an impressive campaign to save the lake. That campaign includes monitoring of lake chloride levels and initiatives to reduce chlorides used in winter services in the watersheds that feed the lake. This effort has garnered broad-based support from a coalition of state and local governments, private and public service providers, universities, regional businesses, leading snow and ice industry associations, and manufacturers. The last example is Flint, Michigan, where after switching to the Flint River as a new water source, the elevated corrosivity of the river degraded aging water pipes, allowing lead to leach into the city's drinking water. The failure to follow anti-corrosion protocol in the switchover triggered the problem. However, Mark Edwards, the leading expert investigating the case, attributed the runoff from salt from winter services to be the primary reason the river chloride levels were elevated in the first place. Experts caution that other municipalities with aging infrastructures that pull their drinking water from inland lakes and rivers are increasingly at risk of similar outcomes if more sustainable practices are not adopted. This problem is very real, and concern over it at the state and local level is only going to increase. The failure on the part of both private and public providers to follow best management practices for the storage and application of road salt is at the root of the problem. This causes excessive chloride runoff into surface and groundwater, causes infrastructure damage, and damages vegetation and runs into our storm drains, ending up in our water systems. A decade ago, several studies were done to try to determine where the chlorides were originating from: the private sector that services parking lots and sidewalks, or the public sector that services roads. At the time, the public sector was attributed to be about 60% responsible versus 40% for the private sector. But as urban expansion escalates and the land is transformed from greenscape to concrete, by recent indicators, those percentages have now reversed. To get a better understanding of the role of the private sector, let's take the highest best management practice application rate for dry salt from the New Hampshire Green Snow Pro certification program at 430 pounds per acre and compare it to the amount of salt that contractor said was appropriate to apply to a customer's property to achieve acceptable results. 80% of contractors surveyed exceeded the best management practice rate. 60% more than double them. The truth is that most contractors don't know how much salt they are spreading, either because they don't have the tools to monitor and control the application of materials, or they don't perceive it to be a necessary function of their business. Contractors have some valid reasons for over-applying salt, and others that just don't continue to make business sense. They include liability concerns and hold harmless agreements, lack of knowledge and training on more sustainable and cost-efficient snow and ice control strategies, failure to monitor and control salt output, and reluctance to change. However, Largely due to the impacts discussed earlier, regulation and enforcement actions have been growing, and sooner or later, private contractors are going to have to adopt more sustainable salt management practices. In 2016, SIMA added sustainability to its core values, cautioning contractors to prepare for regulation. According to the 2016 Snow Industry Benchmark Report, the number of contractors who considered government regulation to be their company's biggest external threat increased by 10% in 1 year. Because liquid strategies have been proven to substantially reduce the salt application rates required to achieve service goals by up to 75%, they can significantly reduce the amount of chlorides being released into the environment at a substantial cost savings to the contractor. Anti-icing is the most environmentally safe and cost-effective practice in winter maintenance. It requires about 1/4 the material and 1/10 the overall cost of de-icing. The time to act is now. Early adoption of salt-efficient practices provides time to prepare and to integrate the new services into operations in a phased plan to ensure their success. The alternative, to wait until change is mandated, could prove costly. The most important strategy to add to the operations toolbox, and potentially the most cost-effective, is DLA pre-treating. It is important to use specialized equipment properly calibrated to apply the right amount of material in the right place at the right time. And lastly, monitoring, controlling, and documentation of material output is critical to achieving continual improvement in your application processes and optimal return on your investment. The market for more efficient liquid services is expanding. Consumer groups for whom sustainability is a growing priority include hospitals and clinics, universities, colleges and private schools, public school systems, publicly funded organizations, upscale commercial, residential, and retail properties, properties near environmentally sensitive areas, resort and retirement communities, and LEED certified properties. There are many business advantages in adopting more sustainable liquid practices. Among these are that they reduce salt usage, the associated costs, and resulting environmental impacts. Adopting them now positions you to be optimally prepared for regulations. Lastly, liquid technology provides your company with a competitive advantage for a rapidly growing sector of the consumer market for whom sustainability is a priority, and establishes you as innovative professionals on the leading edge of the industry. Thank you for your interest in liquid solutions. For more information on how you can reduce your salt usage, cut costs, and improve outcomes, please see our operations modules on liquid pre- and post-treatments and pre-wetting.